Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. Today we're going to go over Unit 4 Energy Question 2. This is like the 5th time I'm recording this video, so hopefully this is the one that goes through. Okay, so we've got this frictionless surface with a box, 20 kilograms, and it's moving to the right. And there's a wall here with a spring attached to it. And the box comes in and it compresses the spring. And then the box comes to a stop. And then the spring pushes back on the box, so it kind of goes back and forth because of the spring. So it'll oscillate back and forth, okay? A couple things. Does the spring does work on the box indicate whether that work is positive, negative, or zero? The spring does negative work on the box, okay? Couple of things. The spring pushes in the opposite direction the box is moving. And so that would be negative work. Okay. Another way to think about this is initially here, we have some kinetic energy, and in the final we have zero kinetic energy. So 0 minus, remember, work is equal to the change in energy. So when it went from some energy to no energy, that means we have to have negative work to cancel out that positive energy. Okay. I would have also accepted 0 because it really depends what you define as the system, and they didn't tell you what the system was. Okay, so if you, I feel like if you argued, if I'm just looking at the box as a system, then there is negative work done on the system. But if I include the box and the spring in the system, then there is no work being done because the spring is part of the system. So the spring cannot be doing work. Okay. Alright, I'm going to be doing this on the previous slide, but calculate the magnitude of the work described in part I. Okay, so we already have our equation here. Work is the change in energy. Okay. Change in energy is the final energy minus the initial energy. Okay. Remember at the end we said there was no energy because the box is not moving. And initially we have some kinetic energy. Okay. And what's the formula for kinetic energy? It's 1/2 mv squared. So it's negative 1/2, the mass is 20, the velocity is 4 squared, and you get negative 160 joules. Okay. Perfect. Calculate the spring constant of the spring. Okay. So, if we were to include the spring as part of the system, then we know that this kinetic energy is transferred into potential spring energy. Okay. So we know that the kinetic energy equals potential spring energy. Kinetic energy we just said was 1/2 mv squared. Potential spring energy is 1/2 kx squared. Okay, and let's rearrange for k. The 1/2s can cancel out. So that's mv squared over x squared equals k. The mass was 20. Velocity was 4. And the displacement of the spring was 0.5 squared. That should equal k. And so k came out to be 1280. Units are Newton per meter. Okay, perfect. Okay, calculate the magnitude of the maximum acceleration of the box. Right? So we can find acceleration from F equals ma. Okay. Now, what is the force that is causing this box to accelerate? It's the spring. Okay, the spring is pushing on the box which causes it to change its velocity. And so, this is force of spring equals ma. And if you remember, the formula for force of spring is kx equals ma. And so we get the greatest force of spring when we have the greatest displacement of the spring. And we said the maximum displacement was 0.5. Okay, so that means acceleration, let's rearrange for acceleration, is kx over m. And so that means acceleration is, we found k to be 1280. X, we said, was at the maximum 0.5, and the mass was 20. And so A came out to 32 meters per second squared. Okay, I know we're on the energy unit, but they threw you a harmonic motion question here. Calculate the frequency of the oscillation of the box. Remember, for harmonic motion, and they give us two equations in the equation sheet. The first one they give us is the period of a spring is 2 pi square root m over k. And then the second one they give us is the period of a pendulum is 2 pi square root the length of the string divided by g. So remember, we were talking about this, how the period of a spring is only based off of the mass of the object and the spring constant, whereas the period of a pendulum is only dependent on the length of the string and the gravitational constant. Okay, so we're going to use, since we're dealing with a spring, we're going to use the period of a spring. Okay, the period of a spring is equal to 2 pi, and then the square root of the mass, and the mass was 20, divided by the spring constant, which was 1280. Okay. Now, once you find the period, just remember the period is just the reciprocal of the frequency. Okay. So once you find the period, you can just find the reciprocal to find the frequency, and the frequency for this came out to 1.27. The frequency is in hertz. Okay. 1.27 hertz. Alright, let x equals 0 be the point on the box when the box makes contact with the spring, with positive x direction toward the right. On the axis below, sketch the kinetic energy of the oscillating box as a function of the position. Okay? So here's the wall, here's the floor. Okay? Here is the spring. Okay? The box is coming in and it hits the spring right here. Okay? And then the box pushes the spring in so that the spring is compressed. Okay. And then after that, it's going to oscillate back and forth, right? So then after that, the spring will push on the box so that it's like this, okay? The box comes in, it pushes it in, and then it gets pushed out. And then it goes back and forth between these three scenarios. On the axis below, sketch the kinetic energy of the box. We know that at this point and at this point, what are the velocities at these 2 points? The velocities at these 2 points are 0. And the velocity at this point is the maximum, right? It's going to be traveling the fastest right in the middle. Okay? So we know the velocity here is 0. The velocity here is 0. And here we have some sort of maximum velocity. So your graph should look something like this. Okay? Perfect. And now we are sketching the acceleration. Okay? acceleration. So let me redraw our three scenarios here. So again, here's our wall, here's our spring, here's our box, and this is when it first hits the spring. And then the box is going to be here, and then the box is going to be here. Okay, so it's oscillating back and forth. When the spring is here, when the box is here, the spring is pushing this way. And when the box is here, the spring is pushing this way, okay? So we're talking about acceleration, and we know that force is directly proportional to acceleration, right? These two are directly proportionate. Okay, if you have force, then you have acceleration. If you have a negative force, then you have negative acceleration, okay? So at this point here, at the 0.5 meter mark, we have a force to the left, or a negative force, so we will have, let's do this in another color. We will have some sort of negative acceleration. And when we're over here at this point, we know we have a rightward force, we have some sort of positive acceleration. And we know right in the middle at the equilibrium point, there is no force. And so no acceleration. So your graph should look something like this.